Happy Friday, everybody. Today we are going to continue talking about population growth. And today we're actually going to get into some of the equations and some mathematical modeling of how populations change over time. So before we start, it would be a very good idea if you have access to the equations and formulas sheet, which I just pulled up on the screen here. You can find this posted in Google Classroom. Today we are basically going to be covering all the information in this section. This is the second page of the equation and formula sheet. The first equation up here is just a rate equation. This basically is just calculating the slope of a line, which we're not going to spend too much time on today. dy over dt basically means the change in y over time, which is frequently the x-axis. So if you're looking at a rate of change, you're looking at how quickly some y variable changes over time. We are going to focus on the equations on population growth and then exponential and logistic growth. So have this somewhere that you can access it as we move through today's lesson. To start out with, I'm going to give you a problem to consider. You can use those equations on your equation and formula sheet to help you figure out where to start on this. But read through this question and give this a shot and see if you can figure out the population growth rate for this population. When I approach a problem like this, first, I'm going to go through and just pull out some of the important information. So in 2006, the United States has a population of about 300 million. So this is my initial or my starting population size for this problem. If there were 14 births and 8 deaths per 1,000 people, so there's the rest of my data, what was the country's net population growth that year? Ignoring immigration and emigration, which of course in the real world are pretty substantial. Well, this gives us births and deaths, but the calculation here would be a little tricky if we try and go from millions to per 1,000 people. So the first thing I'm going to do is I'm going to convert the birth rate and the death rate to a per capita number, so per person. So if we have 14 births per 1,000 people, that means for every one person, the per capita birth rate would be 0.014. We can do the same thing with the death rate. It says there are 8 deaths per 1,000 people. So that's a per capita death rate of 0.008. And so, of course, our net population growth is going to be the number of individuals added through birth minus those subtracted through deaths. So the overall rate is going to be births minus deaths, which is going to be 0.014 minus 0.008, which, if my math is right, is 0.006. So that's my per capita rate of increase of this population. So now I could take that 0.006 times 300 million, and that would tell me how many new individuals were added to the population that year. I'll let you do the actual math, but I wanted to just get that idea out there of converting this to kind of a per capita number. So now we're going to get into the equations for exponential and logistic population growth. And hopefully you watched the crash course video last night, so you have a basic understanding of what those two types of population growth are. If not, pause this video and please go back and watch that 11-minute crash course video from last night so that you're ready to continue talking about these two types. We're going to look at the equations for calculating population growth in an exponential situation and a logistic situation. One important thing to remember is that when we're talking about these equations, you do need to be able to do the math, but maybe more importantly, you need to understand the concepts and always think about kind of how the numbers that you're plugging in apply to an actual population and what that actually means. So we're going to start by just defining some variables. And I know the equation sheet lays these all out for you, but I do want to talk through them because it will help you understand the equations that we're about to look at. So the first one up here is a capital N. N is just, you can think of it standing for number, but it's the population size. It's the number of individuals in the population. N at time 0 is your initial population size. So it's the number of individuals that your population starts with at the beginning of your calculation. Then the third one over here, hopefully you recognize this symbol. This triangle is a Greek letter delta. Delta N means change. That triangle means change in this case, change in population size. The lowercase t, of course, stands for time. That's something you've probably seen before. And over here we have delta t. So that's a change in time, or you can think of it as over time as time passes. So what we're going to be calculating in most of the equations today is the change in population size, delta n, over delta t, over time. Change in population size over time. You will notice in these equations that the notation they use is a little bit different. They use a notation that is frequently used in calculus, so it may or may not be familiar to you, but instead of writing that triangle for delta, they put up a lowercase d. It means the same thing. It means the change in population size over time, whether they write it with a triangle or with the d. So don't worry about those little letter d's. This right here is what we're trying to figure out. That is the rate of growth of our population over time. You'll also see some r's in these equations. The capital R is just the overall growth rate of a population. But the overall growth rate actually isn't a very useful number. Because like we did in that starting question, it's much easier to do math if we can have that on a per capita basis. So we don't use that one very much. We use lowercase r, which is the per capita growth rate. In other words, for every individual that's currently in this population, how many more individuals will we have in the next generation? You also have this variable k down here, which stands for carrying capacity. And carrying capacity, again, is the highest amount of individuals that an ecosystem can sustain over an extended period of time. Not the maximum it ever reaches, but the highest that can be sustained over an extended period of time. Now let's get to the equations themselves. The first one here is the equation for exponential growth. So you can see here we have that dn over dt. This is basically how many individuals are going to be added to our population or lost from our population if it were negative over time. So it's the rate of change of our population. And you can see exponential growth. The equation is fairly simple. If you remember, exponential growth on a graph looks like this. It just goes up and up and up and up. Because all that happens is we take R, that's the growth rate of the population per capita, and we multiply it by the number of individuals in our population. So if the growth rate is 0.5, for every one individual that we have now, we'll have another half an individual. I know that doesn't make sense in a reality kind of way, but in a mathematical way, we'll have another half of an individual in that next generation. So for example, if our population had a growth rate of 0.5, and let's use some easier numbers, if we started with 100 individuals, then to figure out the number of new individuals that would be added, there we go, we would take 0.5 times 100, which means we would have 50. And you have to remember when you're calculating these, you're calculating the change, not the total population size. So what this 50 means is 50 new individuals. So to find the new population size for the next generation, we'd have to take 50 plus the original 100 that we had. So now our population has 150. Then to calculate our next data point, we'd multiply that by 0.5. And this population will continue to expand and expand and expand. Exponential growth does happen in nature. It happens if there is a new area that some organisms move into and there's plenty of resources and space and no competition. It can happen if there's like a fire, forest fire that clears out an area. Again, you have kind of uncolonized territory. that other species can move into. Exponential growth happens with like bacteria that you're growing in a petri dish that have plenty of resources and they just grow and grow and grow and grow. So this does happen. It's not, it can't continue forever and ever, but you do sometimes see exponential growth in nature. Much more frequently, though, we see logistic population growth, which on a graph looks kind of like this. Organisms first start to increase really rapidly when there are plenty of resources, but eventually they start to kind of level off as they reach that population's carrying capacity, the maximum number that can be sustained. So when we look at the mathematics of this, you can kind of see all of that in the equation. The first part of the equation right here is the same as the exponential growth equation, right? The rate times the number of individuals, the rate of growth times the population size, which makes sense because especially at the beginning here, this population is growing exponentially at first when there's plenty of stuff available. But eventually, the rate of growth, the slope of this line, starts to slow down as we get closer to the carrying capacity. And so there's this other part of the equation that incorporates that idea of changing growth rate as we approach carrying capacity. So if we break down that k minus n over k, remember k stands for carrying capacity and n is the number of individuals currently in our population. So if we look at this, the k minus n part, if we just choose a value, say we're talking about this point in the graph right here. K minus n, so here's k, and here's n. It's showing us basically how much more room, if you want to think of it that, how many more individuals this ecosystem can sustain. If we take that number and divide it by k, by this whole thing, we're basically just turning that into a fraction. So we're saying, you know, where I drew this red point, we might have roughly half of the carrying capacity left. So this takes into account that carrying capacity piece. And there are a couple of interesting things to note about this. First of all, when n is very small, I want you to think about what this value would be. What is that k minus n over k going to be close to if n is really small? When n is really little, way down here towards the beginning of our population graph, it's pretty close to 0, right? So let's, just for ease of mathematics, let's assume that's 0. It's not quite, but it's close. K divided by k, that number is going to end up being pretty close to 1. So then if you look back at our original equation, if we just have the rate of growth times the population size times 1, that's basically our exponential growth equation, right? So that tells us when n is low at the beginning, our population is growing exponentially. And it's going to continue like that all the way up to maybe about there. Then, as n approaches k, then this part of the equation, that k minus n over k, this number, the n, is starting to get closer to k, which means the difference between the two is getting much, much smaller. So this number gets very tiny. And if that number is really small, then our rate of growth, the whole equation, is going to start decreasing. And you can see that again in the graph. This next section, the slope of our line starts to decrease as we approach carrying capacity. And then the last really interesting piece here, let's get some fun colors, is think about what happens when n is equal to k. Then, what would this part be equal to? Well, if k and n are equal, if you subtract them, you get 0, right? So, when n equals k, there's no population growth, which should kind of make sense, remember, for thinking about this in the real world, because that means this population has essentially reached its carrying capacity. And you can see in the graph, it kind of levels off across there. It doesn't mean the population's not changing. A normal population will go up and down, but it'll maintain right around that carrying capacity level. We're going to work with these population growth equations, particularly the logistic growth equation, a little bit more in the activity that you're going to be doing today. When you finish watching this Edpuzzle, there's a document you're going to open up called And So It Grows. There's a little introduction, and the first few questions are just some review of the concepts that we just talked about. And then when you get to part 2, it's going to ask you to use a spreadsheet that's attached to the post today. Hang on, there we go. And I want to just show you that spreadsheet real quick. When you open up that spreadsheet, it's going to look like this, what you have on your screen. You will need to make a copy of this before you're allowed to edit it. So make a copy of this for yourself. And then as you read through, you follow the instructions in the And So It Grows document. The only things in this document that you are going to manipulate and change are these 3 numbers in the top boxes here. This is set up with an initial growth rate of 0.5, a carrying capacity of 300, and an initial population, this, I couldn't figure out how to make a subscript on there, that should be like that, of 2. When you go in and change those values, if you change the carrying capacity to 1,000, you can type that number in the box and click enter, and then you will see the graph shift to reflect the new data. There's nothing else that you need to do. You just type in the numbers and hit enter, and it will show you what that population growth would look like. Pay attention. They're all going to have basically the same shape, but notice how the numbers on the X and Y axis change, and also notice how much time it takes that population to reach carrying capacity and start leveling off as you answer those questions. Feel free to contact me if you have any questions, and I hope you have a great rest of your Friday and a wonderful weekend.